about heat transfer in the last few lectures, including the lecture last to last week, which was the last session I took, where we discussed about heat conduction and the concept of thermal resistance and the equivalent of Ohm's law for thermal resistance, that the so-called heat current or rate of conduction of heat delta Q by delta T equals to the temperature difference divided by thermal resistance. Okay. So we will continue from that point onwards today, and further we will look at the last part of this chapter of heat transfer, which will be radiation. So let's continue ahead. And after completing radiation at some stage, when we are doing the doubts, etc., I will pick up the questions which you might require to discuss from the common test which happened last Sunday. Okay, so let's continue ahead. So just as a quick recap, we will see what we discussed in the last session, which was about from heat transfer. We were talking about conduction. And we saw that if we have a generic type of heat conductor, like one which is an isotropic material, so it has a uniform isotropic conductor, like a metal of this isotropic nature or uniform nature. So it has a thermal conductivity K, a cross-sectional area of A and length L. Okay, and we subject it to a situation where it is placed across a temperature gradient through two constant temperature reservoirs, and also it is of course insulated from outside. So the outer surface is insulated, so heat only flows along the length of the rod and does not escape from the surface. Okay, so this is insulation. In that case, we saw that at steady state there is a uniform rate of conduction, or what we call a heat current. So we saw that at steady state there is a uniform rate of conduction or heat transfer delta Q by delta T, which is equal to the thermal conductivity into area divided by length into the temperature difference. Okay, and there is also a uniform temperature gradient which is given by delta T by delta X is equal to T1 minus T2 divided by L, that kind of situation. Okay, so these are the two important properties of steady state for this kind of a conductor, where it is isotropic and having uniform cross-sectional area. Now this equation, we can see, we can generalize it more into a equivalent of Ohm's law for thermal conduction as opposed to electrical conduction. So we can make it that the heat current is equal to the temperature difference divided by thermal resistance. Okay, so we introduce these two new terms, and from that we saw that by comparison of this equation with this equation, we saw that the heat current is equal to delta Q by delta T in watts, right? And the thermal resistance is equal to L upon Ka in Kelvin per watt.
Sir?
Yes.
So then how is this equation related to V is equal to IR, the original Ohm's law?
Yeah, this is how it is related. See, what is happening here is, you think of this like a heat resistor, no? So it has a thermal resistance, and we are placing it across, instead of a potential difference, we are placing it across a temperature difference where T1 is greater than T2. So there is a heat current flowing through it. So this diagram, okay, this one here which I made above, this corresponds to this equation. Now, what is the equivalent diagram and equation for electrical conduction? It is that potential difference V1 minus V2 divided by, in the case of electrical resistance, if we place this point at potential V1 and this point at potential V2, then if V1 is greater than V2, then there will be electrical current flowing through this.
Yes,
And
sir.
that electrical current is equal to V1 minus V2, or what we write as basically V, but V is the potential difference divided by electrical resistance.
V is equal to IR.
Now in
Yes.
this, and in this is dq by dt. So it is in coulombs per second, and that is what is called ohms. Sorry, that is what is called amperes. Okay, coulombs per second or amperes. And above it was in joules per second or watts, right? And the electrical resistance is rho L by A, which is the same thing as L upon sigma A. So sigma is electrical conductivity, which is the inverse of resistivity. And we just saw that thermal resistance is L upon Ka. So again, you see that these two formulae are also, equivalent of each other. Electrical resistance depends on electrical conductivity, length and area. Thermal resistance depends on thermal conductivity. So
K is the constant over here.
Yes, K is the material property here.
Material property.
Just like material property, which for an isotropic material will be constant. Just like here, electrical conductivity sigma is a material property. And as long as we are talking about isotropic material, sigma will be uniform everywhere. And sigma is 1 upon rho. So that is how the two are. Yes, that's how the two are related to each other. Understood, no?
Yes,
the thermal current equation and the the electrical current equation, they are related like this.
Yes, sir.
So yeah, generally we write the Ohm's law equation like this, but in that, what is the meaning of V? V is the potential difference. So that is only we can write it as V1 minus V2 if the 2 points are at independent potential V1 and V2, right? Okay, so all these things we have seen, and we have seen the series and parallel combination of resistors and all that also. Now that part is pretty important, so I'm going to do one or two more examples of combination of resistors. Okay, before we move on to the integration examples which we are doing earlier. So combination of resistors, but only in this case we're talking about thermal resistors. So you have series and parallel. So in series, remember you have the formula that equivalent resistance is R1 plus R2 plus whatever number of resistors are in series. And in parallel combination, we have the standard formula that equivalent resistance is such that it is 1 by R1 plus 1 by R2 plus like this, sum of reciprocals, the whole thing to the power minus 1. Or you can say that 1 upon R is equal to 1 by R1 plus 1 by R2 like that. Okay. So let's see an example now related to this. So suppose we have this kind of an arrangement. We have two metallic rods like this. Okay. Then two more like this. Okay. And then one of a different material, but connected like this. You would have seen a lot of questions in HCV also of this type. Now this point A is kept at a temperature of 400 Kelvin, and this point B is kept at a temperature of 100 Kelvin. Okay. Now these resistors in between, they are all made of a certain material which has thermal conductivity K1. The blue colored ones, and the other one, which is this one here, it is a different material, it has K2. And also these ones have length L. Okay. Then this one has a length of 5L by 3. This one also has a length of 5L by 3. Whereas this again has a length of L. So like this. Or let's say this one has a length of 2L. So my diagram is not exactly to scale. Okay, the middle one should be longer. Anyway, so these are all metallic conductors, okay, of uniform cross section. All of them have the same cross section. That is all 5 of them. So that area of cross section is 10 centimeters square. Okay. And given that K1 is equal to 200 watts per meter Kelvin, K2 is equal to 300 watts per meter Kelvin, or yeah, and L is equal to 1.2 meters. Okay. So what we have to do, and all conducting rods are insulated from outside. Insulated from the outer surface. Okay. So we want to find the equivalent thermal resistance between A and B. So this is just like a circuit problem actually. So whether you're doing this type of problem in current electricity later or in this chapter, the methods will be the same. So we want to find, first of all, the equivalent thermal resistance between A and B. Then we want to find out the net delta Q by delta T, that is rate of conduction from A to B. And now the slightly tricky part, we also want to find out if this point here is C, we want to find the temperature of C at steady state. All these calculations actually we are doing the net rate also for this steady state condition. Okay. So this should be fairly routine kind of problem. Just work it out. We are doing this for practice. You know how to do this question. Okay. So the standard method is convert this into an equivalent circuit, right? And reduce it by using the series parallel combination concepts and all that. Okay. So just give this a try, people. We'll discuss. Okay, so I'm just starting with the kind of circuit diagram. You can continue with whatever you're doing in the question. So it's like we have two equal resistors here. Say they are R1 and R1. So R1 is L upon K1A. So we'll calculate that later. Okay. Then we have another resistor, let's say R2 in between. But R2 is, the length is 2L and the conductivity is K2. And it's like this. Okay. And then we again have some different resistance, these two. Because while K is K1, but their lengths are different. So these are, let's say, R3 and R3 each. So each of these R3 is 5L by 3 upon K1A. Okay. So now we can work out these values. So this is 1.2 meters divided by K1, which was 200, into A, which was like this. Okay. So 1.2 into this will become 10 raised by 3 divided by 200. So 12 by 2. Right. So that should be 6 watts per meter Kelvin. Okay. So this is my R1. So similarly, my R2 will become, okay. So I have to just make this 24 by 3, I think, right? So this will become 8. Okay. And this will just become 5 by 3 into the same thing, 6. So this will become. Okay. So you can just verify these values, you should be getting the same. Okay. Now in this point, A is at a temperature given to us, I think it was 400 Kelvin. This point B is at a temperature given to us was 100 Kelvin. Okay. This point C was named, and let us just name these two other points also as D and E. So the first thing we will do is we will combine these two in series. So this will become series, so it will become R3 plus R3. Okay. And then we'll combine that with R2 in parallel. Okay. So next we will say that this circuit is equivalent to this one. So this is some R prime, let's say, which is 2R3. Okay. Okay, now this point C will not exist here because we have combined these two resistors, but D and E will be these 2 points. Okay. So further, this R prime will now become 2R2, so that will become, sorry, 2R3, so that will become 20. Okay. So next what we will do, we will combine these two. So it will become parallel combination of R prime and R2. So this will have an equivalent resistance, let's say R double prime, which will be, can use this, or that is the same thing as saying that. So 20 and 8 in parallel now. So we will get this as 20 into 8 upon 20 plus 8. 7 4s, so 5s. So 40 by 7. So this R double prime will come out to be 40 by 7. Or approximately 5.7. And now last step is very easy. So it equivalently becomes like this. All right, so whatever is the current in the circuit here, so this current is I, the same as the current here is the same as the current going through this whole thing. Okay, and now if this current splits into I1 and I2, and that's the same current splitting here into I1 and I2. So first of all, we will see that I is equal to TA minus TB divided by the whole resistance across EB. So that will become TA minus TB divided by 2R1 plus R double prime. Okay, so that is becoming 400 minus 100 divided by, now R1 was 6 as you can see above. So 2 into 6 plus this R double prime is 40 by 7. So this is approximately 300 divided by 17.7, right? Okay. So first of all, we are getting two of our answers over here. The first answer for what is RAB, equivalent resistance across AB, that is our 17.7, or you can say 12 plus 40 by 7 to be precise. Okay, watts per meter Kelvin. That's the first thing. Okay, and the other thing is the heat current which is going across AB, delta Q by delta T net across AB. That is nothing but I in our diagram. So that's this thing, 300 upon 17.7. So that will be approximately.
So 16.93.
Okay, 16.93 watts, right?
Yes, sir.
Okay, correct. 16.93 watts. Okay, so that's got our second answer also. So these are the simple things. Okay, now you have to think carefully how you will find the temperature of the point C, which is not in this diagram. It's in the diagram above this one. So I'm coming to that. So for that, the hint is you first find out the temperature of either the point D or the point E. Okay, and then again you find the temperature of the point C. So you first either find out the temperature of the point capital D or capital E, and then you find, you know, this current I1 across this resistor, either DC or, you know, CE. And from that, by applying Ohm's law to that resistor, you can find the temperature of the point C.
Sir, can we take a series combination from A to D and D to C, and then that will give us our R equivalent for that for A to C?
No, we cannot take A to D plus D to C because the current is not common in R1 and R3. You can see now.
Yeah.
ये जो current I है वो split हो जा रहा है ना in I1 and I2. So that's
So
why
we have to do a
see.
parallel also.
Yes. So what we have to do is we have to understand how the current is splitting, okay, between I1 and I2. So that is where we have to apply what is called the junction rule over here at the point D, okay, or at the point E. So now see in this diagram, okay, so I'll basically just take this here below. So first we'll concentrate on finding the temperature either at the point D or at the point E. Then we'll come back to how to find the temperature at the point C, okay. So in this diagram, see, you can understand what is happening is that your current I is equal to I1 plus I2. Okay. So that you can understand by applying conservation of heat at the point D over here like this. So this incoming heat I should be equal to the outgoing heat I1 plus I2, or you can apply the same at the point E, where the incoming heat is I1 plus I2 and the outgoing heat from here is I. So that's how we are getting this equation. You can see, and you can apply this at D or E, whichever of the 2 points. So this equation is clear now.
Yes, sir.
Okay, now you see across the resistor R prime, okay, which is basically this thing. What is the equation that oh wait, before that, okay, the equation is basically that I1 is equal to TD minus TE divided by R prime. Okay.
Yes, sir.
And similarly across R2, my equation is becoming what, that I2 is equal to the same temperature difference, they are in parallel, but divided by the resistance R2. ठीक है ना? So
Yes,
remember,
sir.
in parallel combination, the current splits. If you take the ratio of these two, na? So I1 by I2, the current splits in inverse ratio of the resistance. Okay, so in general, na, if we have, let's say, RA and RB like this, okay, and some current I is coming like this, so this current will split into IA and IB. So always the equation will be like this, that that I is equal to IA plus IB. Okay, whereas the ratio of IA is to IB will be inverse of the ratio of the resistances, like this. Okay. So for example, if RA was equal to 3 ohms, okay, and RB was equal to 2 ohms, then RA is to RB will be 3 is to 2. So that means the current ratio will be how much? The current ratio will be 2 is to 3. Okay, so in this case, the current ratio would be equal to 2 is to 3. Okay, so that means IA would be 2/5 of I and IB would be 3/5 of I. In this case, okay. Now coming back to this case, so यहाँ पे क्या हो रहा है? The ratio of the resistances is what? Now, if you remember, R2 was I think how much? 8, right?
Yes, sir.
And R prime कितना था? 20, right?
20. Yeah.
Okay, so this is how much? 4 2s are 4 5s are. Okay, so I1 is to I2 is equal to 2 is to 5. Okay, and I1 plus I2 is equal to I. So that means I1 is 2/7 of I. Okay, so this is one thing we'll have to keep in mind. Okay, so this will come in handy now. Why? Because we will apply, we'll go back to the earlier diagram and we'll apply it to the resistor DC or the resistor CE. Okay, so just note down this part first. Okay, then we'll come back to that. So this is a technique which is very important in this type of questions, and later it will be important in current electricity chapter also. So it's like you're learning the same thing, which will help in 2 chapters. Okay, so from that one thing we are getting this current I1. Okay, we know the value of I, so we can use that later. Now the other thing is, from the same diagram, I also want to find out the temperature of the point D. So temperature of the point D में कैसे निकालूंगा? So for that I will look at the equation across resistor R1, which is basically across AD. So for that I'll have what? That the current in that resistor, okay, I1 or I, that should be equal to how much? The temperature difference TA minus TD divided by the resistance R1. So now here it is the other way around. I know TA, I know R1, I know I, and I have to calculate the value of TD. Okay. So going back to this, my I was how much? It was 16.93, right?
Yes.
So it's a little bit tricky calculation, but whatever. 16.93. Okay, so this should be equal to 400 minus this temperature, which is unknown, divided by my R1, which was I think 6, right? Okay.
Yes, sir.
Yeah, so from this I will get the value of TD first. Okay, I'll get TD as 400 minus 16.93 into 6. So that will come out to be something. We'll just calculate this. Okay, and then we will apply the same technique now, like we are doing across R1 over here. We'll apply that same technique now across that R3, which is between D and C. So we'll get the temperature at the point C. So it's a 2-step process.
Okay.
Okay.
So, sir, for DC, we have to take I1, right, as our current?
Yeah, for
Heat
DC
current.
we'll have to take I1, and that is why I have calculated I1 over here. Otherwise I1 की जरूरत ही नहीं पड़ती है ना. If I was only
sir.
calculating the temperature of the point D, then I would not need I1. So if I needed temperature at D or E, I didn't need this. I just needed the value of I, which I have got. But because I have asked to calculate the temperature of the point C, so that's why the question is becoming a little more complicated, because I have to calculate I1, then I have to calculate the temperature at the point D or E, whichever, and then again apply this Ohm's law kind of thing. Okay.
Okay, sir.
Okay. Just complete this calculation. So this will give us nearly 300, actually, close to 300. Yeah, 298.42. Okay. So now these two data I'll have to use, this one and this one. Both these things I will have to use for current across that branch DC. And from that, I will find the temperature at the point C. Okay, so these two values are clear now. Temperature at the point D here and this current I1, how we got. Okay. Now we will go back to this diagram, the one which has the two individual resistors R3 and R3. So in this diagram, we have now calculated the value of I1 and we've calculated the temperature of the point D. So the unknown quantity is the temperature of the point C. That's what we're going to do next. So we will apply this across DC. So we will have the current I1 is equal to TD minus TC divided by R3. So I1 is nothing but 2 by 7 of I. Okay, this is nothing but 298.42 minus some unknown temperature divided by R3, and R3 was 10. Okay. So again, a bit of lengthy calculation, but okay, so this is finally giving us a temperature of T. Okay. Now there's one more little trick we can use, and that's also very interesting trick. I'm coming to that. Okay. Note down this method first and see if you can figure out there's some trick we can use. Okay. So I'll give you a hint for that trick.
So that's Kelvin, right?
Oh yeah, sorry, that
Yes,
is
yes.
correct. That is Kelvin. Okay. Temperature is given to us in Kelvin. Correct. Okay. Yeah. So the hint for my trick method is that look at the branch. Look at the branch DCE. No, that triangular branch on top. Okay. And see that there is some symmetry. That is, DC has the same resistance R3 and CD has the same resistance R3. So can you make use of that symmetry and make this a little easier to solve?
So DC and C.
CE, yeah, sorry. DC and CE. Both of these are R3 each. So what that tells me about the temperature distribution between these 3 points, C, D, and E, or rather D, C, and E, इनके बीच जो temperature differences है.
Temperature at C will be the mean.
Yes, very good. It will be the arithmetic mean of D and E. Okay. Now, just like we had easily found the temperature of D, we can also easily find the temperature of E. उसके लिए मुझे I1 निकालने की जरूरत ही नहीं है. मुझे I पहले से पता है ना? So TA minus TD divided by R1 was equal to I. So from that I got the temperature at D. Similarly, the current going through EB, this last resistor here EB, this one is also known to me na I, and the temperature of the point B is known to me. So from that I can calculate the temperature at the point E directly. So I can avoid this whole thing of calculating I1. So I know the temperature of D and I know the temperature of E. And now because these two R3s are the same, so the temperature at C should be the arithmetic mean. It should be the average value, the mean value of D and E. So we can use that as a trick method also. Okay, so just note this down first, then I will come to that method also. So this is exactly the same type of tricks and methods we'll be using in solving circuit problems in current electricity also, involving series and parallel combinations. So, together this has a lot of weightage, these type of circuit problems, whether they are heat circuits or thermal circuits, or they are like electrical circuits later. Okay, so that's another thing we can use, that we can see that because of the symmetry, okay, I1, which is TD minus TC divided by R3, is also equal to TC minus TE divided by R3. So from this equation, you will realize that the temperature at the point C will become by 2, okay, like this. And now further, you can easily calculate the temperature at the point D using the equation. Okay, so from this we can calculate the temperature at the point D. And similarly, this temperature difference divided by the same resistance R1 is equal to the same current I. So from this you can calculate the temperature at the point E. Okay, and once you've calculated these, you can substitute this here. So finally from that you can calculate the value of TC. So that is another shorter, this is a trick method.
Okay.
Okay. So if you go through the heat transfer chapter in HC Verma, you will see that there are plenty of questions which are these kind of circuit diagram kind of things. So you can try these out. Okay. But of course, for JEE advanced level, apart from the circuit diagram questions, it's very important to do the integration based questions where the conductor is not isotropic. So when we cannot use the formula, so if either K is non-uniform, that is, the material is anisotropic, like the question we did last time. Okay. Or the shape of the conductor is such that the area of cross section is not uniform. Again, like the question we did of the spherical shell and all that last time. Then this thermal resistance is equal to L upon Ka. This formula cannot be used directly. This formula cannot be used. So in that case, we have to use instead integration has to be used. Instead, thermal resistance is calculated by integration, where what we have to do is we have to calculate the equivalent thermal resistance by integrating the thermal resistance of some differential element. So this becomes the resistance of a differential element. Just like in center of mass, you have seen how to take differential elements where you have to use integration, or in moment of inertia calculation, you have seen that you have to use integration and you have to divide your object or body into differential segments or very small elements which are called differential elements. So same thing over here also. So let's look at another very standard example of that type today. We have seen a couple of examples last time also. Okay. The shell case and also the case of the cylinder with a variable value of K we had seen. Now today we'll take this kind of a shape. It is called frustum of cone. It's like if you take a solid cone and cut out a section of it, then the shape you get is called a frustum of a cone. Okay, so we have this kind of shape. It's called the frustum of a cone. So this is a solid metallic frustum. So frustum is basically that kind of shape that you have, let's say, you have a cone like this, and then you cut a section out of the cone. So the shape you are left with, that is called a frustum. So this solid cone, now if you cut out this section, you remove this out. So the shape that you are left with, that becomes what is called the frustum. or sometimes it is also called frustum of a cone. So anyway, we have a solid metallic frustum. Okay. The metal has a thermal conductivity K. It's isotropic. And also, what is given to us that the area of this side, or rather the diameter of this side is 2a, and the diameter of this side is 2b. Okay. So the cross sections at either end have radii of A and B. And also the axial length, that is the length along this axis, the symmetry axis is L. So we have to find the thermal resistance of this frustum for heat flowing from one face to the other face, or from one end to the other end. Okay, so we have to find the thermal resistance for heat flow across the axis, or from one face to the other. Okay, so just try this out. So you have done, for example, this kind of situation for center of mass or for moment of inertia. You know how to slice it, and you know how to divide it into differential elements and then integrate. So the same thing now you have to do, but with respect to thermal resistance instead of with respect to moment of inertia or center of mass. So just try and see what kind of logic you can use here. You can also refer to the question we had done in the last class, where there was a cylinder which had uniform area, but the thermal conductivity K was variable. That type of question, there was one question in your test also, in the common test in the advanced paper. You had a variable value of K, but the same type of logic you have to use here also. Here K is uniform, but area is variable. And in those questions, area was uniform, but K was variable. But rest, the logic is very similar. Okay. So just give this a try, we will discuss. Okay, so I'll just give you a brief idea about how to take the elements in case you haven't started. If you have understood and you're doing the question, you just carry on. Okay, so what we can now do is we can slice it into discs like this. So this becomes a differential element. And now the key thing for us is going to be how to define the area of the disk in terms of the variable quantity. Okay, so if take the distance of the disk from this left face as x, so therefore we'll have to take the thickness of the disk as dx. Okay, but one other thing that will be interesting is the radius of the disk. That will be some variable quantity r. As you can see, the radius at this end is a, and the radius at this end is b. So you can see that r varies, the radius r varies with x, such that r is equal to a at x equal to 0 and r is equal to b at x equal to l. Okay. So this total length was l, of course. So you can understand that the relationship between r and x is a linear relationship, because the shape of the cone is that way. You can see this is a straight line. So if we're just talking about the radius alone, how it varies with x, you can see it varies linearly with x. So you can develop a formula quite easily. The radius varies between a and b as you go along the axis from the point x equal to 0 to x equal to l. That is the point. So from this you can see that this relationship between r and x is such that r will become a plus b minus a by l into x. Now how I got this formula? I'm using the standard concept of equation of straight line. Y is equal to mx plus c. I'm using that concept here. I have a straight line like this, which has the equation y is equal to mx plus c. So in this, you can see that c is equal to the value of y at x equal to 0. And m is nothing but the slope. So that is y2 minus y1 upon x2 minus x1. So using these two concepts here, I'm relating the value of r with respect to x. Okay. Now, see, the heat is flowing in which direction? The heat is flowing in this sort of direction. So the heat is cutting across the thickness dx of that thin disk. Okay. So this is how the heat flow is happening. So for this kind of heat flow along the axis, the thermal resistance of that thin disk, so this is our differential element. It is a thin disk which is of thickness dx and radius r. So cross-sectional area is pi r square. So this differential element now has a thermal resistance of dx upon Ka. So that is dx upon pi r square, where the relationship between r and x is like this. So where r is equal to a plus the slope b minus a by l into x. So we've now reached that situation where we have defined the thermal resistance of a differential element. Now next we have to do the integration to combine all these disks one after the other. Infinite number of such disks together, stacked together, will form the frustum over here. So for that, my x's value will vary from 0 to L. And as x is varying from 0 to L, the radii of these disks are varying from A to B. Instead of calculating thermal resistance, if you were calculating moment of inertia of this shape, then you would just replace dr with di. And the moment of inertia would have become dm into r square by 2 because it's a thin disk. And dm would become density into volume of the disk. So that would be pi r square into thickness. Okay, so now we have to just figure out the overall thermal resistance, which will come from the integration of this. So basically, this is summation by integration. We are doing the series combination of all these disks. So, this is the summation by integration of all disks from x equal to 0 to L in series combination with respect to each other. So further, now while doing the integration, there's a little bit of trick involved, which is why we are doing this question in, sorry, there's a K also over here. From x equal to 0 to x equal to L. So you can of course bring your K and pi outside the integration because they are constants. But now this looks like a very complicated integration because R is that very lengthy function of x. So that is where the trick we will use is that we won't substitute R. We will not substitute R in terms of x because it's very lengthy. Instead, we will substitute dx in the numerator in terms of dr, which will make life much simpler. Okay, so I'm coming to that. Okay, So we are not going to substitute r in the denominator as this whole thing, because it will become very lengthy. The denominator will become a huge quadratic kind of thing, and we'll again have to re-substitute actually. So to avoid that complication, we will use a trick over here. So instead of substituting r in the denominator, what we will do is we will here A, B, and L, they are constants. Okay. So we can see that r is a linear function of x. So if r is a linear function of x, that means dr should be proportional to dx. So this is the trick we will use. Okay. So what we will do here is from this equation, we'll differentiate on both sides. So dr will become, now differentiation of a is 0. So b minus a by l, or we can differentiate with respect to x on both sides. So it's b minus a by l. So that means that dx can be substituted as l upon b minus a times dr. So this is what we will substitute in the integration. We will substitute this thing in the integration above. So we will substitute this in the integration. And that you will see will make the integration very easy. It will be a dr upon r square kind of integration, which is a one-step integration. Nothing difficult about that. Okay, so let us complete the integration. So now substitute this in the integration above. So we just get the thermal resistance is 1 upon k pi Now substitute dx in the numerator as L upon b minus a into dr, okay, divided by r square. Now notice we'll have to substitute the limits also, because we are now integrating in terms of r. So we'll substitute when x is 0, r's value is a, and when x is L, r's value becomes b. Okay, that we know from the fact that r was a plus b minus a by L into x. So this equation told us that when x is 0, r was equal to a. When x is L, in fact, this equation was derived from that concept only. That
Sir? Hello? Hello?
yeah, I think I just got disconnected. Yeah, Piyush, go ahead. Tell me what was the doubt.
Sir, I was asking you that since we are integrating to find, sir, R, that is resistance, sir. Should it be areal integrals or surface areal integrals, sir? Because resistance is with cross-sectional area, right?
The cross-sectional area is varying, right?
Yeah, but then it would be, sir, areal integral, na, sir?
No, it is not an areal integral, beta. Matlab,
No,
here,
no.
see, it is not like, we are integrating for a moment of inertia or for like that. No? Then, yeah, then we would have said that, okay, if we are dividing it into dm elements and all, in that case, you can see it is actually a volume distribution. No? It's a volume distribution of mass.
Okay. So single line
But see,
integrals. Yeah.
but that applies when we are doing, some kind of integration for mass, like whether we are
Okay,
doing
sir.
for center of mass. So then we are doing integration x dm divided by total dm, or we are doing integration for moment of inertia. So that is dm into r square or whatever. No?
Yes,
So
sir.
then we think whether it is a surface volume or length distribution. No?
So in
But
this
here,
case, only line integral is considered, not the volumetric integral or the areal integral.
in this
Sir,
current
again,
is flowing along the axis. No?
yeah.
So we have to slice it into disks.
Okay, sir. Yeah.
Whereas
Understood.
if you remember the shell question we did last time, the current was flowing radially outwards.
Radially outwards. Yeah.
So that's why we were dividing the shell into thin shells. The thick shell,
Okay.
we divided
Yeah.
it into thin shells.
Yes.
So we have to understand how to take the distribution elements, the differential elements, in terms of how the current is flowing, the geometry of the current.
Geometry. Yeah.
Yeah.
Okay. Yeah. Understood.
Okay. So further, this integration, you can see dr by r square integration is -1 by r. And then the limits is a to b. So on substituting the limits and everything further, we get a very simple answer in this. Yeah, Samarth, you have changed how Samarth, you have understood how the limits can be changed. Now, if we are integrating something with respect to x, like this or whatever, it's some function of r into dx, where r itself is a function of x. So what now? If we are changing the limits, instead now we are changing it to some new function with respect to r, then we will change the limits from x to limits to r. So whatever the value of x initially, it corresponds to some initial value of r. Whatever the value of x finally, it corresponds to some final value of r. So when we change the integrand or the variable of integration from x to r, accordingly we have to change the limits from limits for x to limits for r. Okay, so this is clear, na, Sabat? Okay, because of the minus sign, this will become 1 by A minus 1 by B. So further, this will become L upon K pi AB. Okay, the thermal resistance will become L upon K pi AB.
So
Yeah.
I didn't understand why we changed x is equal to L to I is equal to B.
Yeah, so because see what we are doing now, we are replacing dx in the numerator of the integral. The integral is dx upon r square. I mean, no, yeah. Now we are replacing this dx in the numerator in terms of dr, right? So this is becoming whatever b minus or L upon b minus a, that is coming out dr by r square. Now once we have substituted the dx in terms of dr, what is the variable of integration? It is not x anymore, it is r. No? You're understanding the point?
Uh,
So I cannot substitute the value of x into the value of r. No? So I have to see that, okay, correspondingly when x was equal to 0, what was the value of r? R was a. Correspondingly when x's value was L, what is the value of r? R was b. So to change the limits in terms of limits of x to limits of r, because we are changing the variable of integration from x to r.
okay, sir.
Okay, clear now?
Yes, sir.
Okay.
Can you please explain how you change the r in terms of a equation to differential r in terms of differential x?
Yeah, see how we changed it is relationship between x and r. And that was what? That was like this, that r is a linear function of x. R was a plus b minus a by L into x. So this is a constant here.
Yes, sir.
And this whole thing is a constant. This whole thing is also constant. So now you differentiate both the sides. So differentiation of r on this side is the differentiation of this whole thing, a plus b minus a by L into x now. So this is dr by dx. Okay. And this side it is 0 plus that constant comes outside into differentiation of x, which is 1. So is this much?
Yes, sir. I understood.
Okay. So now the interpretation of this is that a small change in r divided by a small change in x is this constant. So they are proportional to each other. So dr is proportional to dx. Why? Because r is a linear function. So the moment this happens, you have a linear function, you have this relation. If y is equal to mx plus c, that means dy will be equal to m times dx. That is, this is proportional to dx. So that concept. Okay, so hope this example is clear above. Okay, now the final example we'll do today of application of integration in thermal conduction is a very classic example problem of the concept of freezing of a lake or pond or whatever. There is a type of calculation we can do that estimates the amount of time taken for a lake or pond to freeze, or the thickness of the ice layer on top of the pond as it freezes through winter. So let me explain. Okay, so the first thing is, here we are doing a calculation for a type of lake or pond where we are assuming that it's like a rectangular shaped or regular shaped tank of water, rather than a real pond or lake will have an arbitrary shape below the ground level. We are assuming it's got a regular area of cross section. So this is cross sectional area A, that is regular. Okay. Now what's happening is, this is filled with water, and let us say that in the winters it is in Siberian region or something like that. So the temperature outside, so that's the atmospheric temperature, it drops to sub-zero. So let's take in our example, it drops to, let us say, minus 10 degrees C. Okay. So we have to find the thickness of the ice layer that we formed. Now, as you know, ice floats on water, even though ice is the solid state of H2O and water is the liquid state. Ice is less dense, or the density of ice is less than the density of water because of the unique hydrogen bonding, which creates anomalous expansion. As the water's temperature reduces from 4 degrees C to 0 degrees C, instead of the density increasing, the density actually decreases, which is why the density of ice is 0.9 grams per cc and the density of water is 1 gram per cc. So ice actually floats on water. So because of that, what will happen is that as the temperature drops outside and the water starts freezing, the layer of ice that is formed will be at the top. It will not be below. It will be floating on the top. Okay. So this is the situation, let us say, at time t equal to 0. So as now assuming that the outside temperature remains constant, T naught equal to minus 10 degrees C remains constant, which also doesn't happen actually. The temperature varies through day and night a little bit, but let's just take an ideal condition where through day and night the temperature is remaining constant outside at minus 10 degrees C. Water will freeze and a layer of ice will float above the water. So we want to find the thickness of this ice layer. Okay, let's say X is the thickness as a function of time. Okay, this is what we want to do. And for that, we will use the values of the latent heat of ice and so we'll take this as capital L. Okay, and we'll use the value of thermal conductivity of ice. Okay, so I'll give you the values also. This is 80 calories per gram. So I'll tell you in a moment. So we'll do actually a numerical calculation of this and we'll see how the thickness of ice layer varies with time. So what will happen is here going from this situation to after some time, we will see that the ice layer has grown to some value of X. So at some time T, we have water and we have ice above. So if you think about it, what is happening is that initially, let's say, in summertime, the water must have been at some temperature like 1 degree C or 2 degrees C or even something higher. And as the temperature drops to below zero, the temperature of the water in the lake also starts dropping. So it drops all the way to zero because of convection current setup and all that. It drops to zero and the heat radiates out from the surface. But once it drops to zero, instead of dropping to minus 10 degrees C further, the water has to freeze first. Until and unless the entire water is frozen into ice, the temperature will not drop further below 0 degrees C for the water. So it's only after a long time that the entire water has frozen into ice, let's say, then the temperature of that ice will drop further from 0 degrees C towards minus 10 degrees. So while there is water in our system, even though the temperature of the surrounding atmospheric thing is minus 10 degrees C, but the water will exist at which temperature? It will exist at the melting point, 0 degrees C. So if you see this ice layer now, it has now become a heat conductor. This ice layer has become a heat conductor whose upper surface is at temperature minus 10 and lower surface is at temperature 0 degrees C. And because the heat conduction happens very slowly, what we'll have to assume is that the ice layer is always in thermal equilibrium, in steady state. So heat is going off like this. Okay, so this is the heat current, so-called, okay, or the heat conduction. So because ice is a very poor conductor of heat, ice has low value of K. I'll just tell you the value of K. So the heat conduction happens very slowly. So because it occurs very slowly, it's always like the ice is in a steady state. And the ice layer is in a steady state such that you can see your delta Q by delta T is equal to K of ice into X divided by whatever area into this temperature difference, and that temperature difference will become temperature of water minus temperature of the surrounding atmosphere. And also there will be a temperature gradient across the ice, which will be uniform. And that will be this kind of temperature gradient. So as you go up, the temperature is decreasing. Okay. So now the thing is that if this is the situation at time t, okay, what is going to be the situation at time t plus dt? Let's understand that next. So very short time later, certain amount of heat has escaped from the system, from the water into the atmosphere outside. And that heat escape has resulted in what? The thickness of the ice layer would have increased. So in that time dt, what would have happened is the ice layer would have just got thicker by a small amount. So this thickness of the ice layer, instead of x, now it has gone to x plus dx. Okay, because that much heat has flown out. So this extra layer of thickness of ice that has been formed, dx, to form this thickness of ice layer, the amount of heat that has been used, okay, that heat is equal to the rate of flow of heat delta q by delta t into dt. Okay, so this dq is equal to k of ice, sorry, ka by l, not kl by l. So this is that is the heat current. It will be 10 degrees C because this temperature difference will be 10. Into dt. So this extra layer of ice that is formed, this is related like this. Now that extra layer of ice which is formed is of mass dm. How we can relate that mass dm? That mass dm is density of ice into the volume. That is density of ice into area into the thickness dx. Because the volume of this small, the small strip of ice or the small layer of ice that is formed, uska volume kitna hai? The uniform area of cross section into thickness. Okay. So further we can write this as dm is density of ice into area into thickness dx, okay, into latent heat of ice is equal to thermal conductivity of ice into that same area by x into the temperature difference, which is constant, but into time dt. Now in this equation you can see we are relating x with t, but in terms of a differential equation. So when we integrate this, we'll get x as a function of time, okay, and x is nothing but the thickness of the ice layer. So we'll do this calculation further. First, just note down up to here. I'll also give you the values of the various parameters. So first of all, density of ice is 0.9 gram per cc, which when we convert to SI unit, it will be taken as 900 kg per meter cube. So this is the value that we'll use for density of ice. Latent heat of ice, as we already saw, is 80 calories per gram. So when we convert this, this will become 80 into 4.2 into 10 raised power 3 in SI unit, which is joules per kg. So this is this that we'll use, and the thermal conductivity of ice, I will just check the value and tell you so that we do an exact calculation. Okay. So just note down up to this integration step, up to this differential equation step, then we'll integrate it. So thermal conductivity of ice, as I was telling you, it's a very poor conductor. It is about 2.22 watts per meter Kelvin. Typically, metals have conductivity of the order of 100 or more. So you can see that ice conducts much more poorly, and that is why it takes time to freeze. Okay. And typically, in an entire Siberian winter of so many months, also, the entire lake will not freeze. If the lake is of sufficient depth, then it will entirely not freeze. There will be enough water below, and that water will be existing at 0 degrees C and not at -10 or -20 or whatever the outside temperature is. And that is how aquatic life survives in sub-zero conditions. So it is a combination of the two factors. One is the anomalous expansion of water, which makes ice lighter than water, so it floats. And the other factor is the low thermal conductivity of ice. These two factors together contribute into, the
Sir,
survival of aquatic life. Yes.
sir, in KVPY, there was this concept, the anomalous expansion of water and the anomalous behavior of water. What's the difference?
They're the same thing, beta.
They're the
Another
same thing?
name for it. Yeah, yeah.
Okay.
The reason for the anomalous expansion is hydrogen bonding, between
Hydrogen
the
bonding.
H2
Okay.
molecules. Yeah, yeah.
Yeah, ma. Yes, sir.
Yeah, Durgesh, I'll scroll up. I'll come back to this section. Okay. So I've given the data below only for K and all these things. So this is one of those very standard and classic problems in physics that is solved. Freezing of a lake problem, that the time taken for the ice layer to get formed, or the thickness of the ice as a function of time. You'll find this question in one of the solved examples in H.C. Verma also. Okay, so now you can see this equation, area will cancel out and everything else is a known constant. So it's a relationship between x and time. So we have to integrate that relationship to get x as a function of time. And when you substitute these values in SI units and all, you'll see that it will show you that x grows very slowly with time. It takes a lot of time for the thickness of the ice layer to reach a few meters or something. Okay, so let us look at this calculation. How we substitute the value of dq. No? So see what is happening. What you have to understand is the process here. No? At some instant of time, my ice layer was this thick. Its thickness was x at t equal to t. So water. Okay. Now what is happening is that the rate at which heat is going out, that current delta q by delta t, it's uniform, so I can write it as dq by dt. Okay, so that is known to me. Okay, so what is happening is that at t plus dt, from t to t plus dt, how much heat is going out? It is equal to this rate of heat current into dt. So it is that heat current into dt. Okay. So that is equal to Ka by L into temperature difference. That is your heat current into dt. But then what this heat is doing, as the heat is going out, is it reducing the temperature of the water? No, the temperature of the water is remaining stable at 0 degrees. Is it changing the temperature of the environment? No, its temperature is remaining constant at minus 10 degrees. So what's happening in that time dt, a further layer of ice is getting formed, whose thickness is dx. So this is the layer of ice formed in time dt. Okay. So that layer of ice formed, suppose its mass is dm, then how much heat was removed from it to form it? Dm into L. So now see this, these two are related. So that's how that dm into latent heat of ice is equal to the heat current multiplied by time dt. So that is k of ice into area divided by x, because this L is now x, into that temperature difference, that is temperature of water minus temperature of surrounding, into time dt. So that is dm into L. Okay, now dm itself is density of ice into area into thickness. So that's how we are getting this. Is it clear now, Shikhar?
Yes, sir.
Okay. So further, this equation becomes like this. See, it becomes x dx becomes k upon density of ice into latent heat of ice. Area cancels out into this temperature difference into dt. So x dx becomes equal to, if we integrate this, so k was constant, 80 into 4.2 into 10 raised power 3. Okay. Into this temperature difference was 10. Density was 900 in SI unit. Sorry, K was not this. This thing was the value of latent heat. So I'll put in the denominator. And K in the numerator was 2.22, right? Yeah, SI unit. So 0.22 into dt. Okay. So from 0 to some x in time 0 to t, we are having x square by 2 is equal to this whole factor, which I will just calculate and tell you. So this is So from this you can see that therefore for let's say x equal to 1 meter, the time has to be these many seconds. Okay. Or okay. So x equal to 1 meter के लिए the amount of time we require for 1 meter thick layer, which is roughly 3 feet. Okay, 3 feet layer of ice or 1 meter layer of ice, more than 7 days is required at sub-zero temperature like -10 continuously. So practically, like it won't happen like it'll not be -10 continuously. During the daytime, the temperature will be a little higher. During the night, the temperature might be lower also. But anyway, so over months of winter also, you can see the entire lake will not freeze because the depth of the lake will obviously be several meters deep. Okay, so this is the example of the freezing of the lake. So with this, we more or less complete thermal conduction. Next lecture, we'll discuss some doubt problems, if at all. But next, just to give you a heads up, next session onwards, we'll be coming to the last part of heat and thermodynamics, which will be about radiation. Okay. Of course, there is also the mode of heat transfer called conduction, but conduction we will not really be studying in detail. Okay. Just a couple of things we need to understand about conduction. Conduction is the primary mode of heat transfer in fluids. Okay. It involves convection currents, which basically involve convection currents basically involve a rather random motion of uh, fluid molecules from a region of higher temperature to a region of lower temperature. So for example, we have a fluid in a container like this, and we have some source of heat here. So what happens is, whereas the outside temperature T naught, so it's acting like a heat sink, whereas this is acting like a heat source because we are supplying heat from here. So what happens is that the because of the heat source over here, the molecules which are near the heat source, they gain more kinetic energy. So they start moving about faster. So as they move about faster, they start automatically moving about to positions where the kinetic energy is lower. And those molecules in turn, which have having lower kinetic energy, come and occupy this. And this is how the heat content starts distributing over the entire volume of the fluid. Now these convection currents, okay, they are unpredictable. Okay, and they cannot be described by equations. Okay, they are unpredictable because they are caused by molecular translational kinetic energy. Okay, gained from a heat source. Okay. And this process is, it's a random process. So this cannot be predicted by any equations. So convection and convection currents cannot be described or cannot be predicted by any simple equations. Instead, they are predicted by simulation. By complex simulation. Okay, which is not done here. It is done at the engineering level. Okay, so it is not in syllabus, but there's an entire part of engineering which is called computational fluid dynamics, CFD, which is to do with computer simulation modeling of this process of heat transfer via convection. And that is why that is a more complex subject which comes in the domain of engineering. It will not be dealt with us in this domain. Okay, so that is about convection, which we will not be studying in any further detail. Sorry, not conduction, but convection. Whereas conduction we've already done. Okay, so next session we'll be talking about radiation. Now radiation is the mode of heat transfer through electromagnetic waves like visible light, but including more complex electromagnetic waves like infrared, ultraviolet, microwaves, X-rays, etc. All these things, okay, have their own range of heat transfer, but particularly these three: infrared, ultraviolet, and visible light. So that mode of heat transfer is called radiation, and radiation does not involve any material medium. Therefore, radiation creates heat transfer across vacuum. So across vacuum of space, radiation is the primary mode. For heat transfer. So we'll be discussing more about radiation in the next lecture. And with that, we'll wind up this section of heat and thermodynamics. Okay. So that's it for today's session, people. Wish you all the best. Shikhar, to answer your question, no, you don't need to solve questions related to vapor pressure and saturation, vapor pressure and evaporation, because that is not in your syllabus. Okay. So
Yes,
H.C. Verma has a bit of extra things in kinetic theory of gases chapter, which are to do with that evaporation, vapor pressure, saturation, vapor pressure, dew point, fog and all that. So you can read those through those things. They are interesting to understand, but you don't need to prepare them for the entrance exams. Okay.
Okay, sir.
Sir,
Okay. Yes.
sir, should we start solving sums from HCV for heat transfer?
Yeah, you should absolutely. Like you will find a lot of questions which are to do with this circuit type of problems that we've done with thermal resistance, with conduction. So all those problems you can do. Then couple of questions of integration also. So all the things related to conduction you can complete. And then the second half of the problems are to do with radiation. So that you will do after next lecture.
Okay, sir.
Oh.
Yeah, thank you,
Okay,
sir.
people,
Bye,
sir.
sir.
Okay, bye people.
Bye, sir. Thank you, sir.
Bye, sir. Thank you.
Okay, wish you all the best.
Thank you, sir.
Yes, sir.